Is reality an illusion? Questioning space and time. This question has intrigued humanity for centuries, from ancient philosophers to modern scientists. What if everything we thought we knew about the universe was wrong? What if our understanding of reality is just a shadow of a deeper, more complex truth? What if space and time, the very fabric of our reality, were not what they seemed? Could they be constructs of our perception, rather than fundamental aspects of the universe? This isn't the plot of a science fiction movie. It's a question that physicists and philosophers have been grappling with for decades. From the ancient Greeks to contemporary thinkers, the nature of reality has always been a profound mystery. The idea that space and time might not be fundamental, but rather emergent properties of a deeper reality, is as mind-boggling as it is profound. It suggests that what we perceive as reality is just a surface layer of a much more intricate and hidden structure. Our intuition tells us that space and time are absolute and unchanging. We live our lives by the ticking of the clock and the vastness of space around us. Space is the vast, empty stage upon which the cosmic drama unfolds, a seemingly infinite expanse that holds the stars, planets, and galaxies. While time marches forward, an unstoppable river carrying us from the past to the future. It is the relentless flow that governs our existence, marking the moments of our lives. However, this comfortable view of reality begins to crumble when we delve into the bizarre world of modern physics. The more we learn, the more we realize how little we truly understand. Einstein's theory of relativity, which revolutionized our understanding of gravity, showed that space and time are not separate entities, but rather interwoven into a single fabric called space-time. This interconnectedness challenges our traditional notions of reality. Quantum mechanics, the theory governing the microscopic world of atoms and particles, further complicates the picture by suggesting that at the smallest scales, space and time become fuzzy and uncertain. Particles can exist in multiple states at once, defying our conventional understanding. The implications of these theories are profound, challenging our most basic assumptions about the nature of reality. They force us to reconsider what we know and open our minds to new possibilities. Could it be that space and time, which seem so fundamental to our existence, are merely illusions, emergent properties of a deeper, more fundamental reality? This idea pushes the boundaries of our understanding and invites us to explore further. As we journey deeper into the rabbit hole of modern physics, we encounter concepts that are stranger than fiction. Wormholes, black holes, and the fabric of space-time itself challenge our perceptions. We'll explore the mind-bending ideas that challenge our perception of the cosmos. These concepts not only expand our knowledge, but also inspire a sense of wonder and curiosity about the universe, and raise profound questions about the true nature of reality. What lies beyond our current understanding? How deep does the rabbit hole go? Join us as we delve into these mysteries and seek to uncover the true nature of the universe. In the early 20th century, Albert Einstein shattered our classical understanding of gravity with his groundbreaking theory of general relativity. This theory was a monumental shift from the Newtonian mechanics that had dominated scientific thought for centuries. Unlike Newton's view of gravity as a force acting at a distance, Einstein proposed that gravity is not a force at all, but rather a curvature in the fabric of space-time. This revolutionary idea changed the way we perceive the universe and our place within it. Imagine a bowling ball placed on a trampoline. The ball's mass causes the trampoline to sag, creating a curvature around it. This simple analogy helps us visualize the complex concept of space-time curvature. The ball's mass causes the trampoline to sag, creating a curvature around it. This curvature is akin to the way massive objects like stars and planets warp the space-time around them. Now, imagine rolling a marble across the trampoline. Instead of traveling in a straight line, the marble's path will curve as it is drawn towards the bowling ball. This is a simplified analogy for how Einstein described gravity. Instead of traveling in a straight line, the marble's path will curve as it is drawn towards the bowling ball. This demonstrates how objects in space follow curved paths due to the warping of spacetime. This is a simplified analogy for how Einstein described gravity. According to general relativity, massive objects like stars and planets warp the spacetime around them, creating a curvature that affects the motion of other objects. According to general relativity, massive objects like stars and planets warp the spacetime around them. The more massive the object, the greater the curvature it creates. This curvature is what we experience as gravity. The more massive the object, the greater the curvature it creates. This curvature is what we experience as gravity. Just like the marble on the trampoline, objects traveling through space-time follow the curves created by massive objects, giving the illusion of being pulled by an invisible force. This curvature is what we experience as gravity. Just like the marble on the trampoline, objects traveling through space-time follow the curves created by massive objects, giving the illusion of being pulled by an invisible force. Just like the marble on the trampoline, objects traveling through space-time follow the curves created by massive objects, giving the illusion of being pulled by an invisible force. This concept has profound implications for our understanding of the universe. Einstein's theory has been experimentally verified numerous times. It has revolutionized our understanding of the universe. It explains phenomena that Newtonian mechanics could not, such as the bending of starlight around massive objects and the gravitational redshift of light. It explains the bending of starlight around massive objects, a phenomenon first observed during a solar eclipse in 1919, which provided one of the earliest confirmations of general relativity. The gravitational redshift of light escaping from strong gravitational fields is another prediction of general relativity. This effect has been observed in the light from stars and galaxies, further validating Einstein's theory. And then there are black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These mysterious objects are perhaps the most dramatic manifestation of general relativity, challenging our understanding of physics and the nature of reality itself. While general relativity describes the universe on the grandest scales of stars, galaxies, and the cosmos itself, quantum mechanics governs the realm of the very small, atoms, particles, and the fundamental building blocks of matter. These two theories have been the cornerstones of modern physics, each excelling in their respective domains. And when we try to reconcile these two pillars of modern physics, things get weird. The challenge lies in unifying the macroscopic and microscopic worlds into a single coherent framework. At the Planck scale, an unimaginably small distance of approximately 1.6 times 10 to the minus 35 meters, the very fabric of spacetime undergoes a dramatic transformation. The smooth fabric of spacetime, as described by general relativity, breaks down. It no longer behaves as a continuous entity, but rather as a frothy, turbulent sea. This is the realm of quantum foam, a chaotic sea of quantum fluctuations, where spacetime itself is thought to be constantly bubbling, warping, and tearing. These fluctuations are so intense that they defy our conventional understanding of space and time. Imagine zooming in on the surface of a seemingly still pond. The analogy helps us grasp the concept of quantum foam. At first, the surface appears smooth and calm. It seems like a perfect, undisturbed mirror reflecting the sky above. But as you get closer and closer, you begin to notice tiny ripples and fluctuations, a constant dance of energy exchanges. These minute disturbances are akin to the quantum fluctuations in spacetime. This is analogous to the quantum foam, where spacetime is not a static background, but a dynamic entity in a state of perpetual flux. It is a seething, ever-changing landscape at the smallest scales. At such minuscule scales, the principles of quantum mechanics, such as Heisenberg's uncertainty principle, come into play. This principle is a fundamental aspect of quantum theory. This principle states that we cannot know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we know about the other. The more precisely we measure one, the less we know about the other. This trade-off is not just a limitation of our instruments, but a fundamental property of nature itself. This inherent uncertainty at the Planck scale has profound implications for our understanding of space-time. It suggests that space-time is not a fixed, immutable stage, but a dynamic, fluctuating entity. If space-time is constantly fluctuating, then even the concept of a fixed distance or duration becomes meaningless. The very notions of space and time become fluid and uncertain. The smooth, continuous space-time of our everyday experience may be nothing more than an illusion, an emergent property of this underlying quantum chaos. This realization challenges our deepest intuitions about the nature of reality and opens up new avenues for scientific exploration. As we continue to probe the depths of the cosmos, we are reminded that our journey is far from over. The quest to understand the fabric of the universe is a testament to human curiosity and our relentless pursuit of knowledge. Scientists around the world are working tirelessly to bridge the gap between general relativity and quantum mechanics. Their efforts may one day lead to a unified theory that explains the universe in its entirety. Such a theory would not only deepen our understanding of the cosmos, it also revolutionize our technological capabilities, opening up possibilities we can scarcely imagine today. Until then, we continue to explore, to question, and to marvel at the intricate tapestry of the universe, ever diving deeper into the fabric of the cosmos.